Great. Earlier I mentioned the Grape 1. I chuckle when I think about that because that was one of those things that was supposed to be an engineering prototype and never meant to leave the lab. And we've probably got 50 or 60 of them running successfully around the country and around the world right now. But we owe a lot of that and much more to John Gibbons, N8OBJ. John works here at Case Western Reserve University, and he's going to talk about, actually it's now the present, and a little bit more about the future in the Grape 2. John?
Good morning. My name is John Gibbons. My day job is I'm a lab director at the Series Analog or Circuits Design Lab at Case Western. When I first came up here, I thought I was going to be giving a talk to HamSCI, but I guess they changed back to HamSCI, so we're good now. What I've been busily working on for the last eon, it seems, is the Grape 2. Now, Grape 2 wanted to give a brief review of what the Grape is supposed to do. I'm not going to go through every bullet point. The slide presentation was pretty much put together so people could review it afterwards. I don't want to waste too much time going through it, but there are some key points as to what it is associated with its operation. One of the things I wanted to go over a little bit was some of the operational assumptions, some of the Achilles heels of the Grape 2. One, it has to have the 1 PPS signal from the GPS. Without it, the data synchronization cannot happen. So that is key. So you need a good GPS signal. We're assuming that the power is maintained to it. It has an internet connection, and on the Grape 2, it needs to be wired because the case that it is in is a Faraday cage, and the wireless will not get out of the case reliably. We're also assuming you have a grounded antenna correctly, for obvious reasons. And we'd like it to be in an environment that isn't varying wildly in temperature because the GPSDO has a little PID in it, and it's going to be chasing its tail if you keep moving its temperature around. This is a basic architecture. On the top there is the RF deck, which contains the 3 radios, the filters, and the A to Ds for the subsystem. That board plugs into what I call the logic sequencer board, which houses the logic engine that runs the data acquisition system, as well as a built-in magnetometer interface, so you do not have to buy the separate one. In fact, I have bought, or Dave Witten donated 20 magnetometers, and I have them available, so if you on the Grape 2 are getting a Grape 2 and want a magnetometer, just say so, and I will provide it for you. Some assembly is acquired, though. You have to put it in a 1.5-inch PVC pipe and bury it 3 feet in the ground and blah, 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 blah. But there's directions on how to do that. Also, the system has on the bottom there a Raspberry Pi 4B with 8 gig of memory and an external LP Leo Bodnar GPSDO and an external 4 terabyte hard drive for saving data. Now, the system collects an 8 kilohertz sample rate on 3 radios, which is collecting about 48 kilobytes of data per second. It adds up to about 432 megabytes per hour, or about a little over 10 gigabytes of data per day. Adds up quick. The RF front-end board, it started its origins from the Grape 1. You'll notice that there's a resonant filter, and then the mixer and the high-pass filter are basically Grape 1. In front of that, I had to put a buffer amplifier because all the resonant filters would clobber each other if you tied them all together. And then I added in front of that an additional RF gain stage where you can set the gain now from either 1, 2.5, 4, or 10. So you have some latitude depending on your antenna system, where you're at, how you're situated, to adjust the gain of the system for more optimal observations. This gets into the architecture of what the software developed into. Most of this work is thank you to Bill Blackwell. You've done a phenomenal job. I could not have done this without you. There are many intercommunication pipes, processes, etc., that make this thing happen. We first tried running the data acquisition, which is a synchronous data acquisition as opposed to asynchronous like you would do doing recording audio. Synchronous is much more difficult because every 125 microseconds you have to service the A to D and read it. If you miss it, you lose the data. And that's what a lot of people miss on how difficult that is, because having something happening every 128 microseconds is, in an operating system, insane. I tried doing this without the integrated Pico, and on average, we would lose 300 samples per second of the 8,000 that we were taking. So we had to regroup and redesign, and we spent a lot of time getting this to work. I know Bill and I spent better part of 6 weeks getting the Pico to actually be able to grab the data. That wasn't the problem. It was piping it back to the Raspberry Pi and getting it to reliably go through the channel without dropping stuff. The data is checksummed on the Pico. We transfer it over to the Raspberry Pi. It is checksummed again and then written to a file and verified. And if the checksum verifies, at the end of each second, you get a little V. We also store information for each second about the satellite constellation for the GPS, the lock, and all kinds of other fun things that we've encoded into that, thanks to Bill. For the most part, it's a very complicated and interwoven system. When you first start the process up, it takes a good 7 seconds to establish all the intercommunications going on between the programs of the Pico and the Raspberry Pi. So it's very involved and very complicated, but we got it all to work. This is the digital RF deck board. On the left, you can see the input connector, and there's a set of jumpers there. And then you have your 3 resonant filters. Down the center is the 3 mixers, and then to the right is the analog filters, and then the A to Ds. This is the logic sequencer board that the RF deck plugs onto. It has a U-Blocks GPS on it, the logic sequencing engine on it, the Pico in the upper right corner, and I made sure that the backup battery for the U-Blocks was not a primary battery, but a secondary battery, and what that means is it's rechargeable. You don't have to replace it. That's what the board set looks like when you plug it together. Then you put all the pieces parts together. Some assembly required, and that's what I'm finishing up right now. These are the 4 3D printed case parts. Thank you to, I think it's Majid. If I get that said your name wrong, I apologize. I'm terrible with names, but he did a phenomenal job of designing this case. I'm still in awe at his work. It's just amazing stuff. I had selected a extruded aluminum case that we're looking at end onto, and you can see where his case grabs the little rails on the top there. And that whole side's got a radius on it, and his caps match it perfectly. It's just like he did an amazing job. So that is the front. That's the Leo Bodnar that plugs into it, which goes into the front of the case. It snaps into the front, and the leads come out on the side. The back of the case on the top houses the Raspberry Pi. When you put them together, it looks like that. The Raspberry Pi cable then comes out and plugs into the back of the unit where that 40-pin ribbon cable is inside the case. When you put it all together, it looks like that. So that is a Grape 2, which is a 3-channel RF receiver, low IF receiver. It will receive on WWV 5, 10, and 15 megahertz, or it will do CHU 3.33, 7.85, and 14.67, or mix and match. All 6 frequencies are in there, and in the setup program, you set up which ones you want to receive. And that's sitting on top of the hard disk drive. After much consternation, we finally got it to work. We were having extreme problems with the disk drive controller just disappearing while it was taking data. And we went through 4 different controllers to finally found one that worked. So that's another picture of it. Now, getting into the running of the system. This is a shameless plot for the last DMM I had my hands in designing at Keithley. It's a 7.5-digit DMM, but in addition to that, we built in what's called a digitizer. It's a 1 megasample digitizer that has a 100,000 reading buffer, and you can digitize voltage or current. So I digitized the first 100 seconds of the power-up sequence looking at the current. This is the current draw of the Grape 2, fairly consistent. You can see where it's booting. And right around second 61,000, which is about a minute into it, I turned on the data collection. So you can see that jumped up a little bit, and you can see the thing jumping up and down. I don't know if I did. You can show. Oh, here, can you see this? No, you can't see that. Never mind. But anyway, that's the current draw of the Grape receiver. This is what our console is looking like. This presents to you in real time what the Grape 2 data is collecting. I tried to keep it as simple as I could and cosmetically not too complicated, but what it's providing you is for the signal level, the frequency determination, and if you have a magnetometer, it has the middle line is what is currently being read at that second. The line above it is the peak for the 24-hour period, and the line below it is the minimum for the 24-hour period. But we also have the ability to, if you hit Control P for Control Peak, it'll change it to a 1-hour window. Now, the reason I put the 24-hour window into it is you need to know what the maximum gain is to be able to set the RF jumpers down the road to figure out if you have enough gain. I'm shipping all the units with a standard gain of 2.5, although the two I'm shipping to Colorado, I'm setting the gain to 1 because they have a little bit closer proximity to WWV. And they usually don't even need a radio to hear it. But anyways, this is what the console is going to show you as it's running in real time. And this is a plot that I wanted to explain. Part of the synchronous data collection problem we were having is the pipeline between data communications between the Pico and the Raspberry Pi 4B. On the very bottom line with all those black blobs is the actual communications on the USB port between the Pico and the Raspberry Pi during 125 microsecond epoch. Now the line just above it, those little short little blocks there are the 16 megabit SPI transfer of the 6 byte data readings from the A to D. So you can see the data, it doesn't take much time to get up to the Pico, or to the Raspberry Pi from the Pico, but we're already close to maxing out the Raspberry Pi 4B's USB ports. And we took this is running at 8 kilosamples. We took it to 10 kilosamples per second. It worked fine. We took it to 12 and it collapsed. So you're saying, what's going on? Well, there's a lot of interprocessing stuff going on the Raspberry Pi, which is part of the problem with real-time data acquisition with an operating system. Operating system can slush things around and move it around to make a time for the time scheduler and things like that. Like, for example, Linux has what's called a systic, which happens at a kilohertz rate, which every millisecond it comes in and readjusts the priorities of the tasks, does what it needs to do, and gives its operating system back to you. That's why we can't do real-time data acquisition system directly on a Raspberry Pi, because of the systic. If you happen to be in the middle of a DMA transfer and that 125 microsecond data says, come get me, you don't have the bus, you miss the data, which is why we were missing 300 to 500 samples per second when we were trying to run under the OS. So as now, we're just getting to shipping the first Grape 2s. I've got 10 of them ready to go, although on the drive-in this morning I realized there's one setting I haven't fixed yet, but that will get done Monday. But one of the things that Bill discovered why FLDigi skips seconds during the course of the day, typically 2025 seconds. What's going on is that the A to D is giving the FLDigi a 8 kilohertz or 8,000 samples per second. But the math that's being used in the filter requires 8192 samples per second. So every second we have to steal 192 samples from the previous second. If you do the math, about every 42 seconds, that adds up to a full second, and that's why it skips. So one of the things we're going to be doing is kicking the sample rate up from 8 kilohertz to 8192 hertz to solve that problem so that FLDigi doesn't cause the skip. But that's what's going on with why they have to interpolate every 40 seconds for the math on the collected data from FLDigi. We're also looking at compressing the raw data for possible transfer to a repo. The headless boot, we're having some problems. It sometimes, without a monitor on it, it wakes up in 320 by 480, and then when you VNC into it, you got this huge start button and you can't see anything else. So we're working on that. Sometimes the boot will also hang on the external hard drive. Of the 10 units or 12 units I've set up so far, I've only had one now that I've had I'm still having that issue. But if you unplug the drive and plug it back in, it sees it and it boots. So we haven't figured that one out yet. We're also talking about adding a graphical console to the Grape 2, which Kung will probably be attacking. We're going to be adding a conversion engine to create the digital RF format to upload to Bill Engelke's database. We're also, I think the U-Blocks can have a 1 PPS holdover mode when it loses satellite lock, but I have not had a chance to look at that yet, and that's on the list of things to look at. And of course, there's other enhancements, improvements, bug fixes, and whatever. One, as a final note, if you're getting a Grape 2 and you want to install a magnetometer, just indicate so, and I will include the magnetometer board. Like I say, I got 20 of them donated by Dave Witten. I actually just soldered 2 of them together last night, and they both came up and worked fine. And so if you want one, let us know. And I'd like to thank University of Scranton, CASE, and the National Science Foundation, all accolades and probably whatever given here. And thank you. Any questions? Sure.
Good. Thank you very much, John. As we've heard a couple speakers this morning, I want everyone to keep one thing in mind. One of HamSCI's core goals is the development of low-cost instrumentation, both hardware and software, to support our research goals.